Hey everyone, and welcome. Today, we're going to do a quick mathematical checkup. We'll take a look at some problems that probably feel pretty familiar, from back in the day, but we're going to look at them through a totally new lens. See, this isn't just about solving for x. It's about pulling back the curtain on the elegant, invisible system of rules that makes all of math tick. So, let's get started. All right, first things first. How would you go about solving this? Don't worry about grabbing a calculator or anything. Just, think about the steps you take. Consider it a little pop quiz to get the brain warmed up. And there it is, 8 plus 16 divided by 4 minus 2. It looks simple enough, right? But what's kind of fascinating is how a problem that seems this straightforward can actually trip a lot of people up. I mean, you've got addition, division, and subtraction all in one go. Where do you even begin?
Well, that's the whole point, isn't it? In math, unlike a lot of other things in life, there's a real, predictable structure. The answer isn't just a matter of opinion. It's what you get when you apply a shared set of rules. So today, we're going to uncover that hidden blueprint.
The best way to think about it is that basic arithmetic is kind of like the language of numbers. It's how we talk about ideas of quantity. And, just like any language, it's got a few different dialects. For instance, you've got the dialect of decimals. This is the math of money, of measurement, super useful for all that everyday precision we need. You just line up the dots and add. It's clean, simple, and direct.
Then, of course, there are fractions. This is the language we turn to when we're splitting things up, right? Sharing a pizza, following a recipe. It takes a slightly different approach. You got to find that common denominator, but it's all part of the same basic language.
And we can even get a little fancier and combine these into mixed numbers. Now, okay, this might look a little more intimidating, but the core system underneath it all is exactly the same. It doesn't really matter if we're using decimals or fractions, the principles hold up. So if arithmetic is a language, you can think of the order of operations as its grammar. It's the blueprint that stops everything from becoming a total mess and makes sure we all understand each other. Let's see how this blueprint actually works. So this is it, the official rulebook. It's kind of like a recipe. If you follow the steps in the right order, you get a perfect cake every single time. If you don't, well, you get a disaster. And in math, this is what guarantees that an equation has one and only one correct answer. Let's see it in action. Okay, first up, we deal with what's inside the parentheses. And inside there, we handle the exponent first. So 3 squared becomes 9. Next, we finish the job inside the parentheses. 20 minus 9 gives us 11. And finally, we multiply by that 4 on the outside, and we get 44. See? Just follow the sequence and it leads you right to the answer. Now, this language of math isn't just about finding one single number as an answer. We also use it to compare things. So let's check out a different kind of mathematical statement. Here we've got 2 inequalities. So, is that first one true? Well, let's see. 1/3 squared is 1/9, and 1/9 is actually smaller than 1/3. So, nope, that statement is false. The second one, though, 0.5 is less than 2.75. Yeah, that's clearly true. It just goes to show you these rules aren't just for solving, they help us make comparisons that are actually correct. Okay, now we're going to go a little deeper. Beyond the order of operations, there are some even more basic rules, properties that are kind of like the laws of physics for numbers. They just work all the time, so much so that we usually don't even notice them. First up is the commutative property. This is just the simple but really powerful idea that 2 plus 3 is the exact same as 3 plus 2, or that 4 times 5 is the same as 5 times 4. For addition and multiplication, the order just doesn't matter. They can commute, go back and forth. So, have a look at this equation. What's the missing number? Well, because of the commutative property, we know that 7 plus 4 is exactly the same as 4 plus 7. The missing number has to be 4. The rule just gives us the answer. Next up is the associative property. This one is all about grouping. It basically says that when you're adding or multiplying a bunch of numbers in a row, it doesn't matter which pair you decide to tackle first. You're going to get the same answer no matter what. So check this out. On the left side, the 4 and the 5 are grouped together. On the right, the 3 and 4 are grouped. To make these two sides equal, what's that missing number gotta be? It has to be 5. See? The numbers didn't change, their order didn't change, just the way they were associated in the parentheses. And here's what's so powerful about these rules. They're not just for simple arithmetic. No way. They are the bedrock for entire branches of mathematics. The same logic applies pretty much everywhere.
Let's jump over to geometry for a second. Just imagine a perfectly straight line. We'll call it AB. Now, let's put a point, C, somewhere on that line. And from that point C, we draw another line straight up so that the angle ACD is a perfect right angle.
So here's the question. What's the measure of that other angle, DCB? Now to solve this, you only need to know one rule. A straight line is always 180 degrees. So if one part of it is 90 degrees, what does the other part have to be? It's got to be 90 degrees too to add up to 180. The system just works. Okay, let's try one more field, set theory. This is really just about grouping things together based on rules. An intersection, which has that little upside-down U symbol, is simply a rule for finding out what two different groups have in common. So if set A has the numbers 1, 2, 4, and 5, and set B has 2, 4, and 6, what's their intersection? Well, we just apply the rule. Find the elements that they both share, and the only numbers that are in both sets are 2 and 4. So the intersection is the set 2, 4. It's simple, it's logical, and it's all based on a rule. So think about where we've been. We started with a pretty simple calculation, and we ended up exploring the grammar and the physical laws that govern this whole universe of math, from basic arithmetic all the way to geometry and beyond.
And that brings me to one last thought. What math really teaches us is that underneath a lot of what looks like complexity, there's often a really simple, elegant system of rules doing the work. It's not just about getting the right answer, it's about understanding why it's the right answer. So my question for you is this. What other systems in our lives, in traffic and language and society, do we count on every single day without ever really stopping to think about the invisible rules that make them all work? Definitely something to think about. Thanks for watching.